might need to charge it a little bit more right now. Okay. So anyway, 2.5 continuity. So what does it mean for a function to be continuous or not? So what I'm going to do right now is I'm going to explain it how I would explain it. Like, let's say if I was getting gas at the gas station and some random guy came up to me, I would say, all right, look, this is a continuous function. You see how it's a smooth road, there's no holes on the road, that would be continuous. But if there's a hole on the road, it would be not continuous. Also, if you have a situation where maybe there's a break in the road and then it picks back up, not continuous. So again, if you have a smooth road, continuous. You're driving, there's a hole on the road, not continuous. Or if there's a hole and then there's a break in the pavement and then you have to come up to this side before you can drive again, obviously not continuous. So you know by looking at a graph if it's continuous or not right away. But you can't say there's a hole on the road on a calculus paper. You can say that to the guy on the street. So I have to come up with the calculus definition of it. Now, the reason why I explain this before I come up with the calculus reason for it is because I want you to know, looking at a graph without even thinking math, if it's continuous or not. Now, the question is, how do you explain it to on a math paper? So here we go. 3 conditions need to be met for continuity.
We can hear you, Professor.
Oh, I wasn't talking. How about now? 3 conditions need to be met for continuity at x equals a. Can you hear that?
Yeah.
Okay. All right. So now, first condition. Limit as x approaches a of f of x. What the heck is going on here? Must exist. Second condition, f of a must exist. So this doesn't necessarily have to be said in this order. Like another professor might write the second condition first and first condition second. That's fine. But the third condition is usually written third, and it actually covers all of it, which is limit as x approaches a of f of x equals f of a. So let's recap. The first condition is saying, hey, the limit must exist. Second condition is saying, hey, the function value must exist. The third condition says, hey, not only do they have to exist, but they have to equal to each other. And really, the third condition actually covers the first 2 in it. So let's go problem. Are we doing so far good? Now, this class will get more enjoyable when we get to derivatives. Give me another week at least. I know limits is not that popular and continuity and all that stuff. All right, so I think I can take the off now. Okay, so I'm not charging it anymore, so it should be good. Is the audio better now?
Yeah.
Yeah, it's better now.
So, were you guys able to understand what I was saying though earlier?
Yeah.
Yes.
Okay, so let's do a problem. is f of x continuous at x equals 3, why or why not?
No, because the at x equals 3, the y value is 2, whereas the line is above that at 5.
Yeah, you're right. You're thinking right. I'm just gonna clean up the how you say it mathematically for you. So yeah, so everyone here, you guys can look at it and say the answer is no, right? It's not continuous. You can look at it because it's obviously there's a hole on the road there. So how you would say it, say your reasoning again, Madison.
Because at x equals 3, the y value is 2, whereas the line, the limit, I guess, goes up to 5.
Correct. That's fine. I'm just going to clean it up a little bit for you. You would say you met the function value is 2 at x equals 3. Yeah. So yeah, and then the limit is 5. Yeah. So I'm going to write it formally for you here. So no matter how picky your professor is, you'll get it right. I'll give you a little bit more leeway though. Let me show you. So what I would say is, here's my answer. I would say no, limit as x approaches 3 of f of x equals 5. But f of 3 equals 2 and 5 does not equal 2. Now, you don't have to write it all like that. You can, if you said something along those lines, Madison, the way you said it is fine. If you said, hey, the limit doesn't equal the function value, I would accept that as well. All right, ready for another problem? All right, so let's do another one. Is f of x, where is this not? All right, is f of x continuous at x equals 4? Why or why not? So you guys try to do this first. Now, I'm assuming you guys all know the answer is going to be no. Now you got to come up with a reason. Give me 1 second while you do that. I'm going to try to see what. 62. Okay. So I didn't know there was a battery on these Apple pencils. You guys know that?
Don't you charge it on the actual iPad? Like you connect
Yeah.
it to the iPad?
You can charge it another way too. So yeah, it has a lightning port where you just charge it, and but it doesn't have. You don't have to charge it that often. It's like $100 pencil, but I mean, I got it from Cal State Fullerton. It's like this iPad is like a long-term loaner. And yeah, that's why I went with the iPad, because Cal State Fullerton was going to give me one. Otherwise, if I was going to buy it, I probably would have went with the Surface, just because it's an actual computer.
I see.
Yeah, so I was looking into it, and I was talking to another colleague of mine at Cal State Fullerton. They're all like, well, why don't you just get an iPad? They give it to you at Cal State Fullerton if you write them and say you need this for your teaching, and we'll, all right.
That's actually pretty cool. I don't know if they do that at Fullerton College though. I don't think so.
No, Fulton College, they don't give you they don't give, I think, I'm not sure.
I know they lend laptops, but I don't know about iPads and stuff. Just like regular laptops.
Some of the full-time professors got them. Like the first semester that we transitioned to COVID. Because I know a couple of my professors got them, but I don't know if they're still doing that for professors.
Yeah, so it oh yeah, but also there's you can also charge the Apple Pencil. It comes with a accessory where you can just charge it into a like a regular wire. But I mean, Apple products are a little overpriced, but they're good products. They're really designed well. All of my computers are all PC. All right. What was I going to do? Oh, yeah, we're going to do this problem. So the answer to this is, the answer is no, obviously. Now, the limit actually doesn't exist, so we're done. The limit as x approaches 4 of f of x does not exist. So therefore, done. It doesn't meet the first requirement. We don't have to go any further because it has to meet all three. Any questions? Any comments? Rachel, when I say any comments, that's your cue to say a comment? No, I'm just kidding.
Would it be correct to say no, limit as x approaches 4 from the left side is 6, and limit of f of x approaches 4 from the right is 2, therefore limit as x approaches 4 of function of x does not exist? Would that be acceptable?
Yeah, that's actually better than my answer because you were more detailed. Yeah. All right, are we good?
Professor, so there has to be a limit, and that limit has to be equal to an actual like value on the graph in order for it to be continuous.
Yeah, so let me do one example of it being continuous. That doesn't look very exciting. Hold on. This dash part is not part of the graph, but at least you can see where it corresponds to. If I ask you, is f of x continuous on or at x equals 3? The answer would be yes. I mean, like, look, f of 3 equals 5. The limit as x approaches 3 is 5. So they're equal to each other. So limit equals the function value. So it's continuous. It's not very exciting.
Got it.
So what was happening when we were doing limits algebraically, now I can explain this because we actually covered it. So when I said limit as x approaches 3 of some expression 2x plus 5, and I said just plug in 3, and if everything works out okay, that's your answer. Well, the reason why it works, because 2x plus 5, that's a continuous function. It's just the line with a slope of 2. So when I know something is continuous, the function value will equal the limit. So what we were doing is plugging in 3 to get the function value. But since the function value equals the limit on a continuous function, that would be your answer for the limit as well. See, that was what was going on in the background.
Yeah, that makes sense.
So it's because when you look at the equation, we know that it's just a solid line, right? Is that how?
Yeah. And by the way, I'm going to actually mention this soon. I was going to. All polynomials are continuous everywhere. So a parabola, so like a polynomial. So that's I was going to say that in a couple minutes from now, but all polynomials are continuous on negative infinity to infinity, the whole real number line. So what is a polynomial? F of x equals, for example, x squared plus 5x plus 10. That's a polynomial. When the exponents are whole numbers, it's a polynomial. When the exponent is a fraction or a negative, that's not necessary. That's not a polynomial. Not saying it's not continuous, but it's not a polynomial. So the statement that I'm making is all polynomials are continuous from negative infinity to positive infinity. So a parabola or a linear equation, or by the way, the 10 has a 10 is the same as 10x to the 0. So that would be a whole number x1, just FYI. So if a polynomial is continuous, that helps a lot, because later we're going to do a problem like, hey, if f of x is continuous, then you can do this. Well, if it's a polynomial, you know it's continuous. That's it. You can say, hey, it's continuous because it's a polynomial.
Professor?
Yeah.
So what happens when it's an asymptote? Are they
So,
continuous?
Yeah, no. So on an asymptote, we're going to talk about that. No, on an asymptote, it's not continuous, but we're going to talk about that. So we'll come back to this again. So let me go over a few different types of discontinuity. So for example, if you have a graph that looks like this, now you don't have to memorize this. I don't ask you questions like, hey, what kind of discontinuity is this? But the book might, and just for your own general knowledge, this is a removable discontinuity. That's just the name of it, because that point is kind of removed from its place. Whereas if you have something like this, that's a jump discontinuity, like the step function. And then if you have something like an asymptote, that's an infinite discontinuity. Now, on an exam, I'm not going to ask you, hey, tell me what kind of discontinuity is this? That's just not my style of question. But this is just for your general knowledge. But what I'm more emphasized on is like, hey, is this continuous or not? Tell me why or why not. So to answer your question, yeah, so you see this third example with the vertical asymptote there? That's an infinite discontinuity. So if you have an asymptote, yeah, it's discontinuous at that x value.
Even if it's horizontal?
No, I'm talking about vertical asymptote. It's horizontal, it's fine.
Okay, all right, thank you.
Yeah, I mean, that's irrelevant. Like if you have something like this, in this case, yeah, I mean, it might be discontinuous here, but the horizontal asymptote is irrelevant.
Okay, thank you.
Mhm. All right, now. All right, so now, all right, what does it mean to be continuous over a whole interval? For f of x to be continuous, on the closed interval AB. Now, as you guys know the difference between a closed interval versus open interval? Okay. Closed interval means it includes the endpoints. Open interval does not include the endpoints. So let's say if I were to give you the closed interval 2 to 5, that means everything from 2 to 5, including the endpoints. Whereas if I give you the open interval 2, 5, which looks like this with parentheses, that means everything inside 2, 5, not counting the endpoints 2 and 5. So everything from 2.0001, which doesn't make sense because it could be even something smaller than that, all the way to like 4.9999, right before 5. So you can't say 4.99 because there's always some number between 4.99 and 5. Basically not, so this right here, parentheses, does not include the endpoints. Bracket does include the endpoints. You guys all knew, I studied that before, right? Maybe you don't remember it, but you studied it, okay? Hopefully, okay.
Yeah, we did.
But Daniel, of course you have. You had me for college algebra.
Of course.
All right. Moving on. So for f of x to be continuous on the closed interval AB, f of x must be continuous at each point on the open interval AB and limit. Let me just go ahead and write this down, then I'll talk. So x approaches a from the right side of f of x equals f of a, and limit as x approaches a, not a, b from the left side of f of x equals f of b. So go ahead and write this down, then I'll explain with a picture. Okay, so here's what's going on. Oops. So here's what's going on. For f of x to be continuous over this closed interval AB from all the way from A to B, what has to happen is it's got to be continuous at every single value that's inside AB here. But well, we can't say you have the same requirement for the endpoint because you're saying, wait a minute, their limit doesn't exist as x approaches A because from the left side, there's nothing going on. So it gets a sort of looser requirement for the endpoint. So just for the endpoint, limit as x approaches A, just from the right side, it has to equal f of A. And for the endpoint for B, limit as x approaches B, just from the left side, has to equal f of B. So it gets a looser requirement for the endpoints just because, you know, nothing necessarily exists on the other side of it. So we can still call this continuous on the closed interval AB as long as these requirements are met over here. That's all. I only mentioned that because when I was a student, I wondered, I was like, wait a minute, how can you say it's continuous over a closed interval? Because at x equals b, there's limit doesn't exist as x approaches b because There's nothing here. Well, it's a looser requirement. There's a theorem somewhere in the book that will say that. Anyway, let's talk about, let's do a problem from the book. Then after that, I want to talk about the intermediate value theorem. Then we got to take a quiz. Now, let's go to 2.5 here. Let's do question number 18 here. F of x equals 1 over x plus 2. 1. Fx is not equal to -2. X is equal to 2. Oh, -2, I should say. And a equals -2. So here are the directions for the problem. Explain why the function is discontinuous at the given number a. Sketch the graph of the function. So we're going to cover in a future section vertical asymptotes and horizontal asymptotes, but you know the author of this book is under the impression that you all had pre-calculus or college algebra, and you remember everything as if you just studied it 2 hours ago. So here's -2. So basically the graph is going to look like how f of x equals 1 over x plus 2 looks like, because that's basically everywhere where x is not equal to -2. Well, what about -2 itself? Well, at -2 itself is just equal to 1. That's what the bottom line is for. So basically everywhere else except for -2, you're going to use that top portion, f of x equaling 1 over x plus 2 right there. So how do you graph 1 over x plus 2? Well, there's going to be an asymptote there. There's a vertical asymptote at x equals -2. Why? Because that's an x value that makes the denominator 0. You'll learn that again later on. Now, you make a little table, and when you make a little table, you'll realize how the rest of the graph looks like. So you would make a little table and say, all right, let's see here. If I were to plug in -3 here, 1 over -3 plus 2 is 1 over -1, which gives me -1. So at -3, I get -1. If I were to plug in -2.1, let's see, I'm going to plug in -2.1 for x, which gives me plus 2. -2.1 here, plus 2 gives me -0.1. So 1 divided by -0.1 is -10. So it's way down here. So it's going to end up looking like this. And there's also a horizontal asymptote on the y-axis here. And this side is going to end up looking like this, if you can just take my word for it for now. Now, you can see that the limit doesn't exist. Actually, the directions say explain why the function is discontinuous. So they already gave it away that it's discontinuous. So the reason here would be limit does not exist. Because the function value does exist. It's equal to 1, that point right there that I drew. So, so the function value is right here that I drew. The limit doesn't exist, so that would be the reason. You would say limit as x approaches -2 of f of x does not exist. And for me to show you how to graph it, you have to know about asymptotes, and we'll talk about that in a later section.
What number is that?
Number 18.
F of x when x is -2.1.
No, f of x, hold on. F of x equals 1 over x plus 2 if x is not equal to -2. F of x equals 1 if x is not equal to -2. Or if x equals.
I think he's talking about the chart, because I had the same question.
Oh, negative, yeah, that's a
When you put,
-2.1. If you plug in
-2.1.
-2.1, you get -10.
Oh, okay. Thank you.
because I wanted to see how it looks like when it gets really close to -2 from the left side. Yeah, I don't really know how I can explain this if you don't know how to graph. Aaliyah, do you have a suggestion?
For what again?
How would you explain this? How would you do this problem if you don't know how to graph?
You gotta know how to, well, for me, I would graph it. But I don't know, something that I would notice is, I don't know if you guys noticed that there would be a vertical asymptote at that point. So then you know that it's kind of gonna go different ways, most probably, but it could also go the same way. So can't
Yeah,
really
it's
tell.
still, even if it goes the same way, it's still discontinuous because the
Because
limit
it's not-
would not be equal to the function value.
Exactly, yeah. For this problem, you could figure it out, but I don't know. You need to know to graph it eventually, though.
Yeah, you got to know how to graph piecewise functions. You got to know that when you have a rational expression like this, like in this case, it's when it's a fraction. Notice once it's simplified, in this case, it is simplified, that whatever x values that make the denominator 0, that will be a vertical asymptote. You covered that in college algebra, but you'll cover it again in this class later.
Professor, does the a equals -2, is that symbolizing the asymptote, or like represent?
No, because the thing is that in the directions of the book, they'll say for problems 17 through 22, explain why the function is discontinuous at the given number a. So they're saying, hey, explain why it's discontinuous at this -2. I mean, it's pretty obvious that that's going to be what the question was going to be from, because that's where the break happens. But they tell you that's the question, that's the x value there that's in question. So that's given to you in these problems, the a value.
Thanks.
All right. All right. So we're going to move on here. So just when you're doing questions like 17, 19, and 21, you got to be able to graph piecewise functions. That's one of the reasons we, now they're not always going to be a fraction like that. Sometimes it might be like a cosine function or a line or an exponential. You just, again, if you need a little bit of help, you can always go to www.desmos.com. But that's not going to graph a piecewise function for you, but it will graph a piece of one function, one part of it, to see how it looks like. Then you got to know from the piecewise, hey, this only applies when x is less than 5 or greater than 5. So more on that later. I got to cover the intermediate value theorem while we have time, and then we got a quiz to follow. So just do the best you can on the homework. We'll have some time to answer questions later. All right, intermediate value theorem. Oops. Or short IVT. So intermediate value theorem is an important theorem for you to know leaving this class, especially if you're a math major, they're going to ask you intermediate value theorem. You're going to prove it probably in upper division math, not in this class. So there was about 6 theorems / definitions in this class that you really want to make sure you know. So if like someone else asks you, hey, so that's just the intermediate value theorem, or that's just this other theorem we're going to do. Maybe you don't remember the details of it, but at least you can nod your head and then go home and quickly look it up. Okay. If f is continuous on the closed interval AB and K is in between f of A and f of B, then there exists at least one C. I don't know why I put the quotes on C. Such that, or not such that. least one C in the open interval A, B, such that f of C equals K. Go ahead and write this down, then I'll talk. All right, so all right, so here we go. If f is continuous on the closed interval a, b, so notice between a and b, this function is continuous, right? And k is got to be some number between f of a and f of b. So you see k here is it's between f of a and f of b. Then there exists at least one c in between a and b such that f of c equals k. And that's what it's saying. So in this case, there's at least one, and here it is. I show it to you in the picture. Now, that's pretty much it. So again, if f of x is continuous from a to b, which it is, and k has to be between f of a and f of b, which it is, then there has to be some value c in the open interval a, b, meaning in between the endpoints, a and b, such that f of c will give you that function value k. Does that make sense? Now, where would this be applied? Why is this useful? Well, for example, let's say I know at x equals a, I have a function value that's down there. And I know at x equals b, I have a function value that's way up here. And I know that f of x is continuous. Well, f of x is continuous, and I got to go from here to here in the endpoints, then I know it's going to cross the x-axis. No matter what route I take, whether it's this way, it's going to have to cross the x-axis at least one time because it's continuous and it has to go from below the x-axis. So in this particular example that I wrote, k would be equal to 0. Let's say, hey, k equals 0. Since it's clearly between this number and this number, I would say, hey, so there has to be some c value where f of c equals k. In that case, would be here. So let me actually do a problem for you, an example where you would apply the mean value theorem. So when you're doing the problems from the book, when they say show using the intermediate value theorem, did I say mean value theorem? I meant intermediate value theorem. We never did mean value theorem. Okay. Using the intermediate value theorem, show that the intermediate value theorem, by the intermediate value theorem, that there's a 0 between these values. So be very careful with the wording. They don't necessarily sometimes ask you to find the zeros because it's too hard of an equation. They just want you to show, meaning prove that there are zeros in between, and you're using the intermediate value theorem. So let me explain to you what I mean. Let me give me 1 second. Let me make sure the homework problems here are that's 53 and 55. It says use the intermediate value theorem to show that there's a root of the given equation is specified interval. So they don't really necessarily want you to, and when if you have trouble with it, we'll go over it. But right now, let me just do a problem here. Suppose f of x equals x squared minus 6x plus 8 on the closed interval 0 to 3. Use the intermediate value theorem to show that there is a 0 on the interval 0, 3, inside the interval 0, 3. So to do this, we have to first establish that the intermediate value theorem can be applied. So I'll write the answer in blue. But since f of x is a polynomial, it is continuous. What's f of 0? That's 0 squared minus 6 times 0 plus 8. Let me make it a little better here. So f of 0 equals 8. Now let's do f of 3. Which gets me 9 minus 18, which is negative 9 plus 8 is negative 1. All right. So notice the endpoints that we're talking about. At 0, the function value is 8 right here. At 3, the function value is at negative 1, which is down here. So k has to be between negative 1 and 8. Is k between negative 1 and 8? Well, if we're trying to find the 0, meaning set it equal to 0, yes, it is. So since k equals 0 is between negative 1 and 8, intermediate value theorem applies. So by the intermediate value theorem, I can tell you that there has to be a 0 between 0 and 3. There has to be a c value between 0 and 3 such that f of c equals 0. Now, so therefore, there is a c. Remember, c is the x value. K is the y value. Therefore, there's a c on 0, 3 such that f of c equals, in this case, 0, since that's my k value. So again, k is the y value, c is the x value. Now, and usually you would just stop there because by the intermediate value theorem, you showed that there has to be a value between 0 and 3 where the function value would give you 0. Now, I chose this example because I can actually find the value for you because it's an easy enough equation. But the book and the homework, you would just stop right here because you it'll be some weird function where you can't do it. So in this case, x squared minus 6x plus 8 equals 0. I'll literally find the zeros for you. Minus 4 and minus 2, so x equals 4 or x equals 2. So you're guaranteed at least 1, and we got 1, the 2. Why am I picking the 2 and not the 4?
Yeah.
4 is outside of 3.
Yeah, it's got to be between 0 and 3, yeah. So C has to equal 2, where f of C equals 0. Remember, I told you we're guaranteed one C in the interval 0 to 3. So at x equals 2 right here, or C equals 2 right there, it's probably where it crosses the, oops, hold on, it starts at 8, doesn't it? 0 gives you 8. So it probably looks something like that. I mean, not the exact graph, but at that value, it hits the x-axis at 2. Again, you might have issues with some of the problems in the homework. Don't worry, just do the best you can. And I did make the fix on 2-3, right? So I add 53A into it, but erase number 39. So we're going to take the quiz now. So for homework, you would finish up 2-3 and do them as much of a 2-5 as you can. And then don't worry if there's a question or two that you're not getting, we'll go over it. So take 2 minutes to regroup, and then we're going to take a quiz. So I'll give you 2 minutes to relax, get your notes out.
Professor, for the quiz, do we have to print anything out, or?
No. So Daniel, if you can't submit it on Canvas because of your internet issues, just email it to me, but that's fine.
Okay, I will. Thank you.
You didn't get it, hasn't worked yet, has it? It hasn't started working yet?
I know I have it running like a program to notify me when it's online, but it still hasn't notified me anything. And I keep checking on the app for.
Have you tried restarting your have you tried restarting your computer or your internet?
Yeah, no, it's the actual service that's down. I got a notification that they're repairing something. It went from 4:30 to 6:30 p.m. today. That's when it'll be up supposedly.
All right, so let's go ahead and get started. So here's what I want you to do for the quiz, by the way. The quizzes are going to work like this. You just take out a sheet of paper. It could be a lined paper. It could be a blank paper. It could be a graph paper. I don't care. You just put your name here and quiz 1. And that's it. Even if you forgot your name, it's fine because you're submitting it on your account. And usually I'll ask 2 questions. So you just put question number 1, you do it, box your answer, and then question number 2, you do it, you box your answer, and that's it. So just for this quiz, I'm going to give a little bit more leeway, but like you see how Omar has it, where I can see his desk area. That's how we want it. Now, keep in mind, I don't need to see your whole desk area. I don't want to see it too closely either, because that would mean other people can see it. So we'll have this as a practice run. If you can't get it right, make sure you get it right by next week. So let's see here. Desiree, that's great. You had the way you had it. Mark, that's good. Well, a little lower, Mark, but yeah. Brian, that's good. Perfect. Brian Gomez. Rachel, well, maybe next time lower it a little bit, but that's good. Taejun, that's good. Yeah. See, Taejun has it perfect because it's not so close where we can see his writing. Yeah, perfect. Is the water bottle helping you but keep up the camera? Oh no, okay. I thought there's something in there in the way there. Okay, that's fine.
Yeah.
All right. Anyway, cool. I can't see a damn thing there. But anyway, you guys figure it out soon. Exam time, I'm going to be more strict on it. Let's see here. Okay. Yeah. Cassandra, yeah, you don't need to show the whole space because what happens is, nah, I don't think I can read your writing, but move it up a little bit so people can't see your paper too well. Yeah. All right. Anyway, we're gonna start. So here we go. The quiz. Please don't do. If you have questions. Okay. No problem, Madison. Just try to ask your questions on a test during a direct message because some people just give away too much information on accident. I don't know how that happens. Yeah, you can use a page of notes. Front and back, that's fine. You can use a calculator. For question number 1, you don't have to draw the graph if you don't want to.
So after we finish our quiz, do we leave the chat and then submit it on Canvas?
Okay, yeah, well, yeah, don't leave the Zoom meeting, but yeah, you submit it on Canvas, and after you submit it on Canvas, double check, make sure you check your submission and that you submitted exactly what you meant to submit. I had one student last semester submit their geology homework on accident because they submitted the wrong file. So you check the file, make sure it's the file that it looks exactly what you meant to submit, and also it's readable. Like, do you think the professor is going to have trouble reading it? Is all the work that you meant to be shown? Is like the second question, half of it is not cropped out. Again, it's your responsibility to check. You can't email me the next day and say, by the way, I just realized my submission, I didn't submit number 2. Well, it's too late now. It's a day later. Oh, hold on. This is a quiz. I'm going to get this right. There we go. All right, so number 1, you have that graph that's provided for you. It's two-parter. Part A, limit as x approaches 5 of f of x. Part B, what's f of 5? Question number 2, graph that piecewise function f of x equals x plus 3 if x is greater than or equal to 0. Is 1 minus x if x is less than 0. So each question is worth 2 points for a total of 4, and then 1 point for just submitting the quiz. So in the future, even if you think you missed both questions, still submit in the paper, you'll get 1 point. And yeah, that's it. Yeah. Yeah, Cassandra, the answer to the question is yes. Yes, you submit as soon as you're done and check your own submission. Oh, I learned how to make the perfect circle, by the way, James. Thank you. Yeah, James, you have plenty of time. Go ahead and redo it. Yeah, so once you're done, just check your submission and you can leave. I'm just answering the questions.